I'm at Erickson. Started working with AE2S in October, and this is actually my first conference, so it's a pleasure to be able to present. And at the same time, I'd like to thank Grant Slick for bailing on this and letting me present at my first conference. So, in addition to that, I'll be presenting on the outlook into potential future regulations, focusing on emerging contaminants and NDMAs. I'd like to acknowledge the following people: Hazel Slutton with the City of Grand Forks, and also all of her staff with the pilot studies that were done, which we'll discuss later. Caroline Russell with Arcadis, she helped in putting together this presentation, and then Adam Zock with AE2S as well, who helped both with the presentation and the pilot studies. Just a quick little overview of the slides I'll talk about today. Basically broken down into two parts. The first part will go through some background and history of the regulations. The second half will be specifically two case studies that we did at the Grand Forks Water Treatment Plant that address ECs and NDMAs. The history of the Safe Drinking Water Act. As he had mentioned, in 1914 they had the U.S. Public Health Services Bacteriological Quality of Drinking Water. Basically those recommendations that were some of the first that were in place at the time. Moving on to 1974, when the Safe Drinking Water Act was first set in place, which was set to protect the public health. Moving on to the 77, when the first water regulations were actually set in place. It was the first time that contaminants were had a national health-based regulation. 1986 was some of the first amendments that had a major impact onto those, as they enforced the number of contaminants that needed to be recommended or regulated at the time. And then moving on to the 1996 ones, which had a major change in the SDWA amendments, especially the contaminant candidate list, the CCL, and the regulatory determination process that followed with that, basically as this guideline to set up primary candidates for contaminants that will future regulations. So currently, the EPA has national primary drinking water regulations for more than 90 contaminants. These 90 contaminants will fall into the following categories. There'll be disinfectants, disinfection byproducts, inorganic chemicals, microorganisms, organic chemicals, and radionuclides. Another huge part of the 96 amendments was the 6-year review, which is the review of these already set in place national primary drinking water regulations, as well as then the EPA CCL list, which I talked about in the regulatory determination list. So first off, the 6-year review process is just a review of the existing water regulations to determine if it's worthwhile to revise the regulation. Revisions of regulations are based on primary 3 categories. New health effects, if technologies come about that make aware more health effects, then this is a cause for a revision of regulation. Secondly, the occurrence of the contaminant in the drinking water. If the occurrence becomes more than had previously been seen, then this increase in occurrence is cause for a change, and then as well as new treatment or analytical methods. As of today, there's been 2 6-year reviews that have been conducted and have had 2 major changes. In 2006, they had a revision to the total coliform rule, and in 2013, they actually revised 4 standards. So the contaminant candidate list, the CCL, is based on a 5-year cycle that the EPA has to perform. It's a list of their unregulated contaminants, which have the potential for future regulation. It's basically their priority contaminants. So every 5 years, they make a list of priority contaminants from which they need to choose 5 or more to make a regulatory determination on. And what this regulatory determination is, it's basically a formal decision on whether to regulate, to not regulate, to issue a health advisory, or to further investigate based on, again, 3 criteria. The first being health effects. The second, its occurrence in drinking water. And the third, the opportunity that regulating this contaminant has to reduce the health risks to the public. This process can also be bypassed if a chemical becomes readily available, if information occurring to those three criteria of health effects, occurrence in drinking water, or if these new techniques become available on an off cycle, they can make an off cycle regulatory determination as well. Some background on the contaminant lists. First off, the first one was published in 1998. It consisted of 60 contaminants. From this list, then they chose 9 to make a regulatory determination on. The regulatory determination actually resulted in the determination to not regulate any of those 9 which they had chosen. The second contaminant list consisted of 51 contaminants. It was basically the 60 contaminants from CCL1 that was not chosen for the regulatory determination, so it was the remaining 51 contaminants. From this, they chose 11 to make a regulatory determination on, and again, they chose not to regulate any of these contaminants. The third list was published in 2009. It consisted of 116 contaminants. This was a more extensive process. It included some more data on contaminants as well as some solicitations from the public for contaminants that may be of concern. So it is a much greater uptaking. As of today, they haven't had any CCL contaminants become regulated. However, they did have a 2011 off-cycle determination to regulate perchlorate, which we'll kind of touch on here in a bit. So looking into the future with the CCLs and some of the regulatory determinations, the preliminary CCL3 regulatory determination is anticipated in 2014. That's been pushed back with some of the government budget cuts. So it's anticipated now to be in 2014, late 2014, with the final one anticipated in 2015. It's unlikely which contaminants may be on that, but as Stephen mentioned, NDMA is up there, as well as chlorate or strontium. Moving on, the CCL4 then, the list of contaminants will come out in 2015. They solicited nominations for contaminants as well. That was ended in 2012, and it resulted in 59 contaminants, I believe. This process for the fourth contaminant list is going to be a little less extensive just due to those budget cuts and just the undertaking that CCL3 had. Some other upcoming regulatory actions. Fluoride has a minimum of 0.7 milligrams per liter that was issued by the U.S. Health and Human Services. That'll be anticipated in 2015. As I mentioned, the perchlorate rule is proposed to have its MCL in 2015, which will be finalized probably 2 years after that. Proposed lead and copper rule, some long-term revisions anticipated again in 2015. Some proposed carcinogenic VOCs, 2015 or later, and then they're upcoming on their third 6-year review of the existing contaminants for which they have drinking water regulations. So now we'll move from a little of the background information on the process kind of into what ECs are and what NDMAs are as far as they pertain to then our pilot study. Emerging contaminants, they're currently unregulated drinking water chemicals or materials characterized by this perceived or real threat to human health or the environment. They can be any of the following: endocrine disrupting compounds, pharmaceuticals and personal care products, perchlorates, unregulated disinfection byproducts such as NDMA, and fluorinated and brominated compounds. As new analytical techniques allow greater detection abilities, some of these chemicals are being discovered in water that were previously not been detected or that had been detected, but now the levels just are of a significant difference than what was expected. What is NDMA? NDMA is an unintended disinfection byproduct in the water treatment plant that uses chloramines for disinfection. It is potentially carcinogenic, and its toxicity is rather high, which is the cause for concern. It is listed on the CCL3. As I mentioned, it's one of the chemicals or the candidates that is likely to become on the regulatory determination list. It's not set in stone, but it's heading in that direction. California has actually gone about, they have set a public health goal of 3 nanograms per liter in their drinking water with an action limit set at 10 nanograms per liter. And this was done back in 2005 and 2006. Another, NDMA might also become regulated, and I had mentioned the third 6-year review is kind of taking an approach that is going to look at a holistic approach at regulating all disinfection byproducts, and so it may also be contained in that if it isn't contained on the third regulatory determination. Some common technology treatment options for both ECs and NDMAs. First, for ECs, granular activated carbon, GAC, has been a proven technology to remove endocrine disruptors and some other contaminants. As well, reverse osmosis can act as a barrier for almost all of the ECs, which we'll look at in our pilot study. NDMA technology, some technologies are most common: UV oxidation with chlorine or ozone, polymer optimization, GAC or powdered activated carbon, PAC, or again, ROs. Moving from a background and history of these contaminants and ECs, we'll move into the Grand Forks pilot study and how we looked at different technologies to address emerging contaminants and NDMAs. Then we'll compare that to how the current Grand Forks plant operates. So first, some background just on Grand Forks. Its source water comes from 2 river sources, Red River to the north and the Red Lake River, as you can see in the table here. The Red River, water quality-wise, is less preferred. I guess you could say the Red Lake River is more preferred, and so their blend shows that it's typically on a year 85% Red Lake River, 15% Red River. Spring flooding is a unique characteristic around the area as well, and Grand Forks shows that as well with your high turbidity waters. Elevated TOCs is very common to Grand Forks. As Steve had mentioned, he had a graphic with maximums as high as 27. This is strictly from 2013 data. TOC concentrations as high as 19 and 14 in the Red Lake and Red River respectively, with your average right around 15 and 11. And again, the Devil's Lake impacts, so the discharge of Devil's Lake has had a huge had been a huge factor in the Grand Forks source water. You'll see in the Red River sulfate levels as high as 680 in 2013 with an average of 360, which is significantly higher than what they had seen in the past. So the city of Grand Forks had probably 10 years ago had begun this process to start looking into new technologies and processes for their new treatment facility. And it began with an evaluation of their current facility just to see how the structure was, how the treatment processes currently uphold the regulations, and how they produce their water quality and if it's up to standards. So they moved from this, they moved into a treatment comparison where they looked at membranes, they looked at conventional treatment. They toured facilities around the area to get an idea of what everybody in the region was doing. And what they ended up deciding basically was that we'll go with a conventional system. And so they went with this OZONE BAC pilot study to address some taste and odor issues and some emerging contaminant things looking into the future. The OZONE BAC pilot study ran then for 12 months beginning in August of 2010. It consisted of ozone, advanced oxidation AOP processes, biologically activated carbon BAC filters, and then post-filter GAC contactors. Here's a quick schematic of the pilot study that was set up down at the Grand Forks Water Treatment Plant. They took water from the recarb, sent it through the ozone to 3 different filters. The first with 3 feet of BAC media, the second with 6 feet of media, the third with a foot of sand and 3 feet of BAC, and then the fourth was set as a mimic of the full scale, which represented the full scale Grand Forks Water Treatment Plant filter. The graphic above will be shown for the next few result slides for both this pilot study and the following pilot study. So I'll take a few seconds here to just kind of describe what the graphic is showing, and then I'll only have to do it once. We won't have to on the others. Atop here, you'll see the influent water. We have the full scale test that we ran, and then the pilot study as well to compare the two. Across the top, then we have the raw water, the two different processes where we sampled full scale, and the different pilot study that we sampled. The first being an ozone dose for primary disinfection. This is in winter. The first filter with the 3 feet of BAC media, the additional 3 feet of BAC media, so the 6 feet of BAC. We have an elevated ozone, and then an elevated ozone with hydrogen peroxide, or peroxone, to evaluate these advanced oxidation processes. Along the left, you'll see the contaminants that tested positive in water samples in the raw water. It's important to note these are simply just X's or indicators that there was a detectable limit. As you go across the board, the concentrations here may be less than what we see here, but for simplicity and just looking at strictly removal, we just went with basically a yes or a no. And so you'll see for influent water, the raw blend in the winter had about 10 contaminants. As we looked at a full scale, we saw very little removal. There was a little bit, and as I mentioned, may have been some reduction, but strictly removal, there was very little. As we look at strictly an ozone dose without BAC, you see that with a dose of 2.2, which is the primary disinfection, you have 7 contaminants that were in your water, whereas with the elevated ozone and the AOP processes, you see an increased removal of ECs. Going then from your ozone with a 2.2 milligram per liter dose into your BAC filter, you see there's very little in winter with your 3 feet of BAC, just due to the properties and the temperature of your water, source water. And then you see with the additional media, you're able to remove quite a bit more of the ECs. Well, the same graphic for the summer results. This time, raw water had quite a few more contaminants in it. However, we did see the same thing with full scale. After recarbon, after the filter, very little removal. Again, ozone for primary disinfection at 4 milligrams per liter, just due to the warm water in the summer. And then on the far right there, your ozone with an elevated dose of 8 milligrams per liter. And you can see we did remove more ECs than we did in the winter. However, it's still quite a bit of ECs remaining in your water. Same filters as before. You have your 3 feet of BAC, your 3 feet of BAC. This was nutrient loaded. We had sampled Grand Forks water and realized it was nitrogen limited. And so we did nutrient load these two. And so you can see that your 3 feet of BAC media had this about the same removal as your ozone did. Nutrient loading your 3 feet of media had improved EC removal, and then your 6 feet of BAC media had almost complete removal of your raw water EC contaminants. Quick summary of the graphics then. Full-scale processes provided little or no removal. Similar pilot results in the summer and winter as that. It didn't matter if it was summer or winter. Basically, the removal properties of the processes at the Grand Forks Water Treatment Plant had no effect on those ECs. Ozone and BAC filtration successfully removed nearly all of the ECs that we saw with that extended media, with the 6 feet of BAC media and some of those nutrient loading properties that we went through. And then additionally, we did some samples were sent to an outside source, and they ran some GAC contactor tests, which showed that we could further improve the EC removal even more than the ozone and BAC had. Looking at ozone NDMA results then, on the left side you'll see full-scale results, which was just sampled right as it left the plant a post filter, a 6-day detention time from a tap source, which was approximately 6 days of detention time, and then another source which was 8 days of detention time. And you can see that as the detention time increased, your NDMA formation, your NDMA concentration increased. So essentially leaving the plant, you have 0, 6 days, you have 5.2, and then into your 8 days or your extended detention time, then you have an increased NDMA concentration. As you move into the pilot study results, filter F310 is the 3 feet of BAC. 6-day detention time, there was non-detect. 15-day detention time, again non-detect. And this last filter 340, was just set up to mimic full scale. And so you can see that without ozone going through what a pilot of the full scale is pretty much the same. And so it basically verified the results from our tests in that we're pretty much matching what the full scale did in our pilot study, so there aren't pilot study scaling effects, more or less. As we move into summer, same thing on the left, we have full scale, we have an increased free chlorine time just due to the properties of the summer. We have a detention of 6 days, and then here 13 days. Again, seeing that increased detention time lead to an increased concentration in NDMA. As we move to the pilot study, filter 310, 3 feet of media, 1 minute of free chlorine time at 6-day detention was 2.8 nanograms per liter. Increasing that free chlorine time with the same detention time decreased our NDMA concentration. Looking at a 13-day detention time, it did increase it, however, not as much in the summer as we had expected. And finally, this last column is the mimicking the full scale, was without ozone, without BAC, and we realized that this limited free chlorine time actually led to these increase and quite honestly fairly high NDMA concentrations. We'd expect that, as we had seen here, when we increase the free chlorine time, we decrease those NDMA concentrations. We would expect to do the same as increasing the free chlorine time. We'd see a result similar to full scale. So some summary of the NDMA results. Grand Forks Water Treatment Plant full scale, it maintains below that 10 nanogram per liter, which we kind of just set as study parameters based on that California action limit. And so it had satisfactory findings. Ozone biofiltration produced NDMA lower than the full scale, as we saw. It's important to note that the free chlorine contact time with NDMA formation, increasing your free contact time with chlorines, decreases your NDMA. However, you get that balance with your THMs and your HAAs. As you increase your free chlorine time, you increase those. And so you have to deal with that balance between your THMs, your HAAs, and your NDMAs. Lastly, I had mentioned it earlier, but an increased detention time increases your NDMA formation, your NDMA concentrations. And in general, your chlorinated disinfection byproduct formation is lower in winter than in summer due to the cold temperatures. So following the ozone BAC pilot study, the city had basically accepted the fact that they're going to go with a conventional treatment plant. They will implement ozone and BAC based on the findings of the pilot study. And that's when we found those Devil's Lake impacts, the high sulfates, the high bromides, the high hardness, which led to a membrane pilot study where we pilot studied inclined plate settler, ultrafiltration UF, and then reverse osmosis, which was a 6-month pilot study beginning in March of 2013. The schematic just walks you through the plate settler unit where we fed it with acid to maintain a pH of 7 for the downstream membrane processes. We dosed a Paccal coagulant of approximately 40 milligrams per liter. And we ran 2 RO units at the same time, both just kind of to verify results, and then at the same time we used 2 different membrane manufacturers to compare the 2 as well. EC results, again, using the same table. We'll see the same things across the top. Influent, we did test full scale and pilot study as well. Contaminants on the left side. In winter ECs this was 2013 as compared to the ozone one, which is 2010, but we did see similar results in the number of ECs in the winter. As opposed to the ozone pilot study, we did see that the full scale was removing ECs. We'd like to contribute this to the fact that our tests were taken late in the year, closer to spring runoff time, and so the city was dosing powder activated carbon, which could contribute some to the removal of these. As we looked then into the pilot study, pre-treatment in UF had very little removal, and the ROs basically removed all of the ECs that were in that source water. Moving into summer, we saw very similar things. We had an increase in the raw water ECs, very little removal through full scale, also very to none across pre-treatment and UF. Moving into your ROs, again, you saw almost complete removal of the ECs. So as a summary there, a similar amount of ECs were found in the summer and winter, as I had mentioned before. Red River contained higher concentrations, as I had said, that it strictly was, if the water was detectable, it was shown in the graphic, it didn't show concentrations. So the Red River had higher concentrations of ECs. However, they were removed in the winter strictly because of the powder activated carbon that we suspect the city was dosing to stay ahead of their taste and odor issues that they see in spring. The pilot study, plate settler and UF removed hardly any of the ECs. ROs essentially removed all of the ECs. And then any ECs that were found in the RO permeate, you may have seen there was the 1 or 2 in the RO results. Those are basically right at the detection limit, and so if they weren't showing up before, maybe 1 or 2 parts had caused it to become a detect, which was shown by an X. Moving into the NDMA results for the RO system. Again, on the left, we'll have the Grand Forks water treatment plant tap water, free chlorine time, and a detention of 6 days. We mimicked that same detention time. Our free chlorine time was minimized just due to what was required with the RO systems. As you can see, RO performed slightly better. Grand Forks still was fairly successful in maintaining less than 10, which wasn't bad at all. However, RO did improve that NDMA removal. Again, on the left, summer results, we have full scale, which seemed to correspond exactly what we had seen in the previous 3 tests then. However, RO results in the summer, we only had 1 minute of free chlorine time in our testing. And so a 6-day and a 14-day detention time showed concentrations of 11 and 15 respectively, which is much higher than this action limit of 10 and can be directly corresponded to this free chlorine time. We anticipate, again, if we increase our free chlorine contact time, we'd increase our THM, HA5s. However, we would lower this NDMA, probably near what the full scale was seeing. Again, with the ROs, the NDMA formation or reduction was less than 10, less than that action limit. So the city is currently successful in their NDMA reduction. Summer NDMAs were greater than full scale results, as I had mentioned, due to that free chlorine contact time, and reducing that or increasing the contact time would reduce those NDMA concentrations. So some key pilot study takeaways. Currently, ECs are of a big concern to the Grand Forks water treatment plant. They showed very little to no removal of emerging contaminants. NDMA-wise, they performed well. They don't seem to have any issues with that 10 nanogram per liter action limit. If that's, say, what the regulations come down as is 10, then they'd be fine. They're not approaching a limit where it's of concern. However, we're not sure if that's going to become regulated or if that's what that regulation is going to be set at. Ozone and BAC, or the BAC filters, efficiently removed ECs and NDMA formation both. And the RO provided an effective barrier for ECs, and we saw that despite the summer testing, if we increase that free chlorine contact time, we can reduce NDMA formation as well. So as a summary, currently there's unregulated contaminants which may become regulated within the future. Currently, if a contaminant becomes regulated, or basically if a CCL contaminant is become a regulatory determination contaminant and then is found to regulate that in a determination, you're looking at anywhere from 8 to 10 years, 2 years to propose a rule, 3 years to finalize that rule, and an additional 3 years for compliance. So you're looking at around 8 years if a contaminant were to become regulated. Currently, the Grand Forks Water Treatment Plant provides little to no EC removal, as Ed mentioned. Full-scale NDMA formation is present, not currently of concern. And piloting proved that both ozone and BAC and membrane technologies, UF and RO, provided viable treatment technology for reducing these NDMAs and ECs. So moving forward, the city is looking at these results and looking at how they can plan their facility for the future. Current processes, the conventional processes, is an effective technology in removing their NDMAs, not so much for ECs. So if you're looking at the future, some of these ECs that may become regulated definitely need to be addressed, and designing a plant for that future regulations, or always keeping that in mind, is the best way to address those. And that's all I have. So if there's any questions at this time, I can take them now. If not, you can feel free to email me and I can send the questions to the appropriate person. Yep.
Most of your raw water data where you listed some of those emerging contaminants, is that Red River, Red Lake? Or?
That's a blend. So it's a typical 85-15 more or less blend that was taken for those. Red Lake River. Sorry. Yeah.
What pH did you ozonate at?
What's that?
What was the pH in the water when you ozonated it?
Does everyone hear the question? What was
okay,
the pH when you used ozone?
For the ones that we had shown, it was 9.3, I believe. But they did look at other pHs.
And then if you didn't hear the previous question, it was the raw water, where was it coming from? 85% Red Lake and 15% Red River.
Correct. Yep. The raw water blend was 85% Red Lake, 15% red. That's what we showed in all of those graphics.
I think he deserves a good round of applause. Thank you, Matt.